Okay. Can you guys hear me? Okay. Yeah, cool. Okay. I think I'm gonna start with, let's see. Let me share my screen, and I'm thinking that maybe we could start to just try to enter instead of the chat in the Zoom meeting. If we use the Slack, then you guys can access that stuff later too. So let's go with that. So yeah, if you guys have comments, then maybe if you put it in the Slack channel for the class, then we can reference that later too, and I can more easily follow up with more comments in the questions. And then there was some office hours yesterday, and it seemed like it's sometimes I can get it can take a little while to help debug stuff. So maybe in future to also maybe simultaneously be answering questions that others might have, we'll just do an open office hours so others can, I can address multiple people's questions, and then it can be just like more of a general share. So yeah, we can go ahead with that. Okay, so I'll keep an eye on the Slack channel while I go through some of these materials. And today, we're in the last module of the species distribution modeling, and we're going to talk about model evaluation. But first, oh no, yeah, there we go. Okay, and first I just want to revisit the overall process here. So when we're talking about species distribution modeling, I know it's kind of it's a lot of maybe new stuff to throw your way. So and a lot of the terminology can in some cases be essentially equivalent. So I want to make sure that you guys know what we're talking about consistently. So there's this book, Habitat Suitability and Distribution Models, by Guisson et al. And they wrote a really seminal paper in like 2000 that really described this stuff. And anyway, this is a nice overview graphic, and we're just going to go through each of these major steps. And this kind of corresponds to the first lab, which was the Explore lab. And there was presence, in this case, indicated by a little X, and then absence, indicated by a little red dot. And then we also got an entire stack of environmental data, whether you was a marine species or a terrestrial species, and that's what we see here for South America. There's that stack. And then you use the raster extract function to then, for each of those observations, whether presence or absence, go and extract the underlying environmental values for each of those layers. And all of that was in service of creating really a simple table. And that simple table has the Y, which is our response variable, and the X's, which are our predictors, otherwise called features. And so the presences are coded as 1, and the absences are coded as 0. And then we've got that environmental values for that given point in that given row as whatever value you had there. Okay, the next step is what we've also been talking about in this modeling workflow, which is once we have the data and we're going to fit the model with training data, that we call it training data because that's what we're using to fit the model. Separately, we can talk about splitting it, but for now, just following along that there's data that looks just like this simple table, gets sent into a fitting function. That's why I put the parentheses there. And we tried a whole bunch of different fitting functions to do this. We tried logistic regression approaches, which were the generalized linear model, the generalized additive model, and then I'm lumping Maxent in with that kind of approach. And then we also tried the decision tree based approaches to fit the model. And all of that is trying to get at this realized niche of where this species is actually observed with respect to those models, or excuse me, with respect to the environment variables. So each of those environmental variables, you have these little response curves or response plots or term plots. They're all equivalent, but it's the value is varying on the x-axis, and then the response is the y, and that's the presence or absence. And that model is just differentiating between where we see the animal versus where we don't. So we generated those absence points as like a pseudo-absence background, and it could have actually been a true absence, or it could also be this background value, which is letting the software choose the area. But we also cropped it within a reasonable range. So the first two steps, one is collecting the data. Secondly, we're fitting that environmental niche model. And then third, we're then predicting out over not just these points of observation where we've already observed an absence or a presence, but over the entire landscape or the seascape if we're doing a marine model. So that spatial prediction part, that's, in this case, it's feeding the new data. So in red, all the X's, but we do not have the Y's. That's what we want to predict. We're using that relationship to then predict on the Y's. So that's, and with most of the models, they actually just use the same function called predict. And because of the class of objects that it's fed into, whether it's a Maxent or a GLM or a GAM or a tree model, it knows like the specifics of like which package and detailed specific underlying function it's going to use to then handle that prediction. So in this case, we are feeding the new data is all the X's, and we're getting out the prediction, which is just the Y. So this is really important that we understand just like the basic concept of, what is the data that we started with? And because we have this Y, we call that a supervised model, because we're fitting the model based on inputting the response into the model. And when I say you model out, it's actually, you can store it as a little object, and it's got all the configuration of understanding the relationships enough to basically be able to predict, given a new set of X, give me Y. And that's why we can feed that model object into the predict function with new data and get a new Y. What we are going to chew on today is all of these steps. And previously we split the model, but we didn't actually use the test data. We just got 80% of the training data. We did do a fit, and in some cases we did a predict in the past labs, but we haven't really done model calibration, and we haven't really done model evaluation yet. So hopefully today you'll see more of that, and this fuller process will become more obvious. Okay, so I don't have good graphics in the way of model calibration, but this is probably the most common approach, is to look at this variance inflation factor. And this is just a measurement of how autocorrelated a given variable is with other variables. So this is your input predictors, your input x's. And the question is, if they're autocorrelated with each other, you can get these problems. And this is also summarized in this other paper, where it's like there's many statistical problems with estimation and bias. And if you fit on one term and they're very autocorrelated, the entire sign of the coefficients on the other term that can be in the opposite direction. It can, rather than having a positive relationship, it can have a negative relationship, which would not give you proper inference on like what is the relationship, let's say, between temperature and precipitation. Well, if temperature and precipitation are highly autocorrelated, then if I'm looking at a sloth that likes warm, wet places, but if temperature and precipitation are highly autocorrelated, it might show up as the relationship between temperature and the presence of sloth might show up as positive. But then when you look at precipitation, it might show up as negative because it's just fitting the residuals. And so that's improper inference. So that this is a way of handling that. And what you basically do is just drop one of your variables that then reduces this variance inflation factor. Oops. Whoa. Come on back. Where did it go? That's weird. All right. Okay, there we go. Okay, and so another way of doing this is more simply, if you're just looking at two variables, one with the other, then you can look at the correlation coefficient. There's Spearman or Pearson's, and it has a 0.7. So the correlation coefficient, it's a little simpler to understand because the variance inflation factor, it starts at 1 and it has no upper limit. So they generally say when you get into a value of 10, you get into trouble. Like it's considered collinear or multicollinear. Correlation is just between two variables at a time. And the sign of the relation, so 0.7 would be a positive relationship between the two variables, one to the other. It could be a negative, and it maxes out at at -1 and +1. So those are the bounds of correlation. And so if the absolute value is greater than 0.7, then it's considered correlated. So we can drop those. And there's this VIF correlation that you'll use in the lab to basically feed it your environmental stack, because we're just going to use the maxent to go through this whole process, and which are your input predictors. And then it will say like, okay, I stepped through the VIF and removed the ones with the higher correlation values so that you don't get correlations of greater than 0.7. And this correlation also shows up on your pairs plot. So it's another way of checking like, okay, before I run this, I see all my input predictors and I have some that are correlated higher than 0.7. And I'll show this in the lab in a minute after the slides. And then after you run the pairs plot with your reduced set of predictors, i.e. like a reduced number of raster layers in your stack, or if you're thinking about it in terms of a table, a reduced number of columns, or if you were taking in your input, or if you're thinking in terms in a formula, the reduced number of x's to the right of the tilde. So all of those are referring to the predictors, the x's. Okay, so then another way, then once you've fit the model, remember we held out that this test data. And what you want to do with the test data is then figure out like, well, how well did the model do with this subset of the data? And because you have not used this test data set in the fitting of the model, it's considered independent. It's not, you're not biasing the model based on whatever data you're using to test it. So it's really important that you do that split before you do anything else with your data, because this is supposed to try to be as independent as possible. And then we can evaluate it. And we'll look at now some of the things we use to evaluate the actual model. So this prediction and evaluation. Okay, so when we're talking about a response of being like a 1 or a 0, it's present or absence. This is called a confusion matrix. So it starts getting really confusing once I say it all out loud. But all we're doing is saying with that test data, that's our observed, that's our truth, right? And then all we're trying to figure out is, do we get truth back when we run the prediction with that data? Are we getting the values we expect? Are we predicting a presence of that animal where we saw that animal? And are we predicting an absence of that animal where we did not, where we had an absence? So this is our truth diagonal. And then the inverse of that is the false diagonal. So if we had a perfect model, that means that we would predict 100% presence, 100% absence, and 0% here and 0% here. That's perfect. And if we had a terrible model, if we actually, you would just flip those numbers. And if you actually imagine, if you have balanced presences and absences, if you just choose a random model, like a random flip of a coin, then you would get basically like 50% in all of these boxes. So this is how we can evaluate how well we're doing in general. And yeah, so this is also called sensitivity. So it's true presences. So a true presence means we have it was observed as a presence and we predicted the presence. A false absence is we observed it to be present, but we predicted absent. So I get confused with these terms, sensitivity and specificity, but they have to do with these rates. They're called rates just because it's like a percentage of however much data goes in. And we've got the true presences over the total number of observed presences. And then we've got true absences over the total number of observed absences. And these are our basic rates. So this is, sensitivity, specificity. And we're gonna continue talking about this stuff. Okay, so this is this thing called a receiver operator characteristic curve, which is a mouthful, but it's basically tuning a dial. And this 45-degree line that would be a random grab of false positives to true positives. Now, the thing is, like, why are we looking at this as I thought we just had these 4 boxes. Like, how are we going from 4 boxes to this whole curve? Well, you could imagine that what you're getting back when you're getting the prediction that you get back so far with our logistic regressions and basically our response term when we do a prediction, it's not 0 or 1. It is 0 ranging to a value of 1. And so the question is, what is the threshold that we then assign it to be a presence or an absence? So everything equal to or greater than this threshold would be considered present, and then everything less than would be an absence. And if we evaluate that along this curve, then you can start to see what its sensitivity and specificity is based on the cutoff value you assign. So same thing. And this curve, it's called the area under the curve. And this is a measurement of how well the model performs overall. So if you just throw a random 1 or a random 0 in there, you would expect to be on this diagonal. And anything greater than that is considered, explaining the variance of the model beyond random, the null model. And so the higher this, the more area this fills out, the better the model. And if you start down here, the cutoff value would be 0. So if you'd say like, okay, everything's 0, and then as you increase that threshold, you're basically covering the entire study area at some point. So you start off with a very range restricted habitat when you then look at that whole area, and then it contracts. And we'll look at this more visually when it relates up to a map. So everything's habitated there. And then somewhere along the way, we want to figure out what a threshold is. And we can basically, the default is to look at what is the maximum deviation from this null 45-degree line. And that's where we're maximizing the sum of the value of sensitivity and specificity. We're trying to, so it's, we're going back and forth. So here was an old example of doing this with predicting sperm whales. And if we just chose a 50% cutoff from the original model output, it would be over here. And that might be too conservative. So we might predict that it's not habitat, and we might actually encounter whales there. Whereas if we use a lower threshold, then you'd predict more habitat in the map. Here's another example, predicting rockfish. And so the original data is ranging from 0 to 1. And this color coding, this is this ROCR package, it corresponds to what the value is along this curve as you change that cutoff value. So, and you can see how as I change that cutoff value, it goes from everything greater than 0.1 being like, we're going to call that habitat. That's very permissive. If you have an endangered species where you want to be very liberal with what you call habitat so as to prevent potential harmful interactions, you might use a lower cutoff than just this little optimal. Whereas if you're less concerned, then you might deviate. So it's contracting that habitat based on the response. And I think this will also make more sense when you start doing it with yours, and when you, when you do it in the lab. So if we look at the lab.
Can you repeat the optimal distance from the null diagonal line? What is, like, that's what we're aiming for? Like, that's our ideal cutoff?
Yeah, that will be, hopefully we'll see this in action in the lab. So let's take a look at that. Oh no, did I have the wrong link? Okay, let's look up here. So the link up here, I'll fix that other link. So let's just go straight to that question. So in the lab, you actually plot that point of the threshold. And you can see this is where it's deviating the most from that line. This is a little bit, it would be, if these axes were had the same distance, it would be a little bit more obvious even that this is the greatest distance from this line. But it's basically trying
to interrupt. It seems like the link on your website is sending us to the Dishes and Trees lab 1C.
Yeah, so if you follow in the upper menu, that one I got right, under labs, and then lab 1D. So yeah, just use the, I'll put a comment here, we'll fix link and schedule to lab 1D, evaluate or not use. Okay, so when we look at this, here's the same table for my model, where this is called the true presence rate is here. So that's how many we observed and predicted from our test data. And then this is how many we observed as being absent and how we did on that prediction. So it's 83% and 85% when we apply this cutoff. So this is here. So when we do this species distribution modeling package, and I will go back and, sorry, I haven't added more text, but I will add text explaining this to you in more detail. You can also click on the link to get the help on this. But basically that this evaluate function is giving us that area under the curve. So if we had other different models where maybe we used a different technique, or we used different different predictors layers, we could evaluate how well it does with this area under the curve. And the higher the area under the curve, closer to 1, the better the model. And then this max true positive rate and true negative rate. So this is just trying to max the sensitivity and the specificity. So it's like becoming the most accurate, weighing those out. And you might actually want to, like I mentioned, change the dial. If it's a really like endangered species, you'd be more concerned. Which would you be more concerned about? A false presence or a false absence? If you're concerned about an endangered species, if you're concerned about under predicting habitat, you want to watch out for which one?
False absence.
Exactly, false absence. So, so you want to minimize then this false negative rate. So where we actually have true presence, but we predict absence. And this is this false negative rate. And so when you look at this, the code, let's just talk about this a little bit more, because it is a lot to wrap your head around, because there's, I mean, it's even called a confusion matrix. There's no wonder. And then there's curves going on, and there's just this gobbledygook of acronyms. But let's just slowly kind of walk through each of these terms, and hopefully that becomes more apparent what they're each referring to. So if we have our points, our testing points, so this is, remember, we split out the data, that's up here. So you guys had the points, and there was a present column in this points data, and then we read that in, and then this is the actual splitting. So we got 80%. We use that present column to make sure we kind of had a relatively similar size in our test data set of a proportion between zeros and ones in our test as our training data set. And so then we got this the error points test. And if we go down here, this is where we filter out for just the presence test, so _P. And this is where we filter out for the absence test. And we get in a format that Maxent likes. So this is now going and doing a prediction and comparing that prediction with our known presence points and our known absence points with our fitted model that we used. We used VIF to reduce the number of predictors in it above, which I haven't looked at with you yet, but just staying focused on this ROC and AUC and confusion matrix. Then we look at this evaluate object, and it's telling us that, okay, our test data set, so I had 1,000 points to start with my data set. I had 80% I fed into the training data set, 20% went into the test data set, so we're about 200. There was a couple of points that got an NA value with the rasters not having a value there, but it's basically 200 points or 20%. And this area under the curve, so that's what we see here, 0.86 for this overall area. So 1 would be absolutely perfect, and its shape would be just a rectangular. So this is, I would say, pretty good because it's pretty close to getting there. And then this is this max true positive rate plus true negative rate gives us this threshold that is the maximum deviation from the null model that is kind of balances the false positives and the false negatives. So this is how, I don't know why this plot, oh, because I added points there. So that's cool. Actually, it's smart because it waited to plot this. So this is the same plot, but it waited to spit it out until I added the points down here. So this is the plot, and the point is that threshold, which I'll get to in a second here. But first, we get that threshold out of this evaluation object by using this threshold. There are other thresholds to use, but here we specify the name of it. And we get the threshold, spit it out. That's confirming we got this right threshold. And then here, okay, what is going on? Well, our Y max V, that is what we predicted. So that was our raster output from above. And I'll go back to that, but you guys already did this step in lab 1B, where you gave it a stack of environmental rasters, and then you gave it a model object. So that was your fitted Maxent model. And this is the predict step, just like all the other predict steps. Except in this case, the arguments are a little bit different because Maxent will actually handle a whole raster stack for you, which is kind of nice. And we get this raw prediction. Now, this raw prediction is what I was talking about, how the response is varying from 0 to 1. So it's not predicting presence or absence. It's not a 1 or a 0. It's predicting 0 to 1. And so the question is, how do we convert that into binary, into a 1 or a 0? We need to apply a threshold. And so that we can get habitat, not habitat, 1 or 0. And so that we can also evaluate the confusion matrix and look at how if we change that value, how it performs throughout the study area. So eventually you get this. When you apply that threshold, you get this distribution. Here are all the ones in green, and the zeros are gray. And that is habitat, not habitat. And so if we take that same threshold, we can extract that predicted raster with our presence points, and we get a vector of values that say, like, okay, for where we observed presence of this critter and coded it as a 1, what's our predicted value? And so with that predicted value, we can then say, is it greater than or equal to a threshold? And the threshold. And if it is, then we get a true value. So this is called a logical operator. So this is going to give us a logical class result of true or false. And we're going to omit the NAs. So this is telling us what is the, of the presences observed, how many true predictions are we getting? And we can do the same thing with the absences. So we had these absence points. We're extracting, basically laying those points over the top of the raster of prediction that's ranging from 0 to 1. We're extracting that value. And then we're saying, okay, I'm using that threshold. I'm going to call anything less than that value a 0. So if it's less than the threshold, and then it's true. So we observed an absence and we predicted an absence, and therefore it's true. So because we're using this threshold, it's only evaluating this here. It's like, that's the cutoff. And actually each of these points along this curve represents a different value of ranging from 0 to 1, which is separate from the axes that is saying how many are we getting right and wrong. And then we're just picking which threshold that corresponds with. So then we can say, okay, to fill out that confusion matrix, we can say how many, if we sum a logical, meaning if it's true and false, it evaluates to a 1 or a 0. So a true is going to give a value. And then we can divide by the length of how many were in that true vector. So it's going to be, this is a p true is a vector of trues and falses and maybe a couple of NAs that get dropped. And then this is then the length of those trues and falses. And so that's our rate. So this is how many we predicted, or we observed were true, and we predicted were true. So that's true positive rate. And then false negative rate. So that's how many we observed were present, and but we predicted false, or we predicted absence. So yeah, so these are the terms that populate that confusion matrix that we see here. So these are the predicted values versus the observed, the truth value, and how well we did. And so yeah, and so we're trying to minimize the errors there and maximize the consistency there. And then we can use that to then convert. So again, this is just, you can use simple math equations, even with like, it's called like map algebra in GIS terms, but you can do that in R just by applying that. So originally this Y max V was 0 to 1. And then we say, is it greater than the threshold? And then that evaluates true or false, which shows up true is a 1 and false is a 0. Okay, so that is definitely a brain teaser to wrap your head around, to be sure. And then I just want to talk about the calibration step. So this is where, if we do a pairs plot, so this is yet a different pairs plot that the Dismo R package shows. So we can actually feed it that whole environmental raster stack. And then it does the comparison between each of those layers. So in this case, each point, so now we've switched gears completely. I was previously talking about evaluation of model performance, and now I'm talking about calibrating and selecting the variables for the model to be used. So just now I'm here, I was talking about here and looking at how much error there is. And now I'm up here. So when we, this is kind of in this exploratory realm where we want to look at like, where do we have correlation? So what's cool about this pairs plot, it's a little simpler than that fancier GG ally GG pairs function. But I think it's a lot more obvious too. So each point in the scatter plot on the lower triangle represents a pixel. And then that it's placed on the X and Y axis according to the two variables it's comparing. And here we see that altitude and bio 1 are highly correlated, 0.9. And you can see that that correlation is how tight the correspondence is of that scatter plot. So that's a problem. So we would want to remove that to reduce the amount of error we see, or the multi-collinearity problem. And the numbers are smaller where there's less correlation. So this guy is also correlated higher than that threshold that we talked about of 0.7. And so is this guy. So if we feed this variance inflation factor, this looks at across all of the variables and how much multi-collinearity there's amongst all of them. And this guy, the altitude one, has the most basically autocorrelation with all the other variables. And that's why it has the highest VIF. And so we can use this VIF correlation function to apply like we want to have a maximum of 0.7 correlation allowed, and it will step through all those variables and then give you a reduced set of predictor variables. So this thing flagged these 2 variables, and now we're left with these 3. So now when we do the pairs plot and we see the correlation coefficient, now it's none of them have a correlation coefficient greater than 0.7 because of that threshold we used. So that's how we would handle the model selection side. And then this is how we handle the model performance side. And I mean, I'm going to go back and add more explanatory text to this. And there are a lot more possibilities how to calibrate and how to evaluate data, but these are the core main ones and the most commonly used ones. So that's the gist of what I want you guys to be able to understand and reproduce with your data sets. Yeah, so I'd love to open it up to questions, and I'll start by looking in the chat, or feel free to jump in. Mm-hmm.
I have some questions, yeah.
Mm-hmm.
So in the fitting stage, we tried like 2 different approaches to fit, right? The regression, the classification.
Mm-hmm.
What's the difference between that, and like, why do we do both, and then in the evaluation we just only use Maxent?
That's a great question. So in the end, you would want to maybe compare different modeling approaches to see which one performs the best. And the most commonly used procedure would be AUC. So the higher the AUC is, the better it is. But maybe you want to have you want to keep it simpler, and you're willing to sacrifice a little bit of AUC to have a simpler model that could be explained with more ecological relationships. So it kind of gets to this. The ELITH paper talks about predictive capacity versus sort of ecological explanatory capacity. And that might be one of the reasons. But generally, and I should have added that as a step here, because we did try all these different modeling techniques, is to then compare the models with something like AUC.
Cool.
I
So
also, yeah.
is Maxent sort of like the standard for like species distribution? Is that why we're using it, or?
Yeah, it's the most commonly used species distribution model. So that's why I had you guys read the paper on it, and and having you run it here. It's also a little bit simpler to feed because you're only feeding the point data, whereas the other techniques, you actually have to extract the environmental data for those points and then feed the table. In this case, you're feeding the rasters, and it does the sampling for you. So it's a little bit simpler to run, so that we can just focus on the concepts of what these involve, as opposed to all the steps of doing that. There's a few extra extract steps, and then feeding of tables as opposed to the rasters. Yeah.
But theoretically, if we were doing some sort of species distribution in the future, we might model out multiple models and test them all to decide which one to use.
Mm-hmm.
Like if this wasn't in a learning situation, that's what we'd expect to do, right?
Yeah. And in a lot of cases, you see this with climate change modeling. There's ensemble models that where you are model averaging, where you can actually combine techniques. And I guess that's considered to be like hedging your bets so that maybe the failures of one model are compensated by the strengths of another. Yeah, but I mean, a lot of times people will just use one, like just use Maxent and write papers on that. But when we're gonna do, I think I had it in, we're gonna do a supervised learning technique with Google Earth Engine, and that'll use a random forest, because that tends to be what's most commonly used to do supervised classification in general. But specifically to species distribution modeling, and this is sort of a specific binary 1 or 0 that we can use like logistic regression style techniques. Yeah, Maxent tends to be the most common. Medical testing evaluation. It's definitely, these techniques are used in the medical as well as any other field, really. Decision tree approaches for time series data. Okay, so that Elith and Leithwick paper also does talk a little bit about extrapolation. And there's almost a paper I was gonna have you guys use. I think I'm gonna post this paper, even though the R package itself is a little wonky. The techniques that it canvasses are pretty interesting. So let's see. So let me just show you what this is about. So in this case, this is a package that tries to do all of the things for you that are generally used and possible with creating an ecological niche model. And so it can do some data prep, it can generate pseudo absences, can use all these algorithms we've been using, and it can even do an ensemble. So I think I'll add this to the assigned reading just so you get a good overview of the other things that are possible. And the reason I brought this up is there is this there's a prediction step that constraint. Yeah, the spatial restriction methods. So these kind of describe different ways where you can, let's see, there might be, they kind of talk about like climate change forecasts. There's a difference between time series in a big way, a big difference between time series where the response variable is where you're predicting as a function of time, versus using an updated set of input environmental layers that are predicted to be occurring in some future time step. So you could do both, but it's a little confusing. So usually what you do with predicting future climate change scenario, you'd use one of these scenarios, like 8.5, I forget what that is, but in the year 2080. But these are actually available in the SDM predictors package. These future environmental predicted habitat variables, but you could constrain them. So the input that you use might it might not extend to that temperature or that combination of variables. And there's this thing called MESS that Elif kind of wrote up that allows you to kind of try to constrain how far out of the environmental space that you fitted the model with that you can then extrapolate to in some future time step. So we could do that. I've done this species distribution lab in the past, I had folks do that. This is specific to the Santa Barbara area, and like a future scenario. And then you could evaluate things like, where did you lose habitat? So in this case, we're seeing sort of a poleward migration and in elevation. This is Santa Barbara County. And so we're losing habitat in the lower latitude, lower elevation areas, and then we're gaining habitat in the higher poleward elevation areas, and then the zeros where it's the same habitat. So yeah, let's see what else. Yeah. And also I need to just make sure that all the packages are installed on Taylor. It's been really helpful to be able to jump in and see the code that you guys have. So when you have problems that you can post on Slack or in the issues on this GitHub. So you can always click to this little GitHub icon and it'll take you to the site, and then you can create an issue in here. And the fact that I can jump on the server and actually look at the errors and inspect the objects is really huge. So yeah, that's great. I encourage you guys to keep using Taylor. Yeah. So what I'll do, unless there's more questions, is well, I'm just going to hang out here at least until 11, and we'll just keep it open. And if you guys, I'll run the install to make sure the packages are installed in Taylor next, after I fix the link on the course schedule, and then happy to field any specific questions. Are there any general questions to kind of go over? I know I need to add more explanatory text on what's actually happening here, and I think it would be good to compare two model approaches, and then I will add more about the lab write-up that will be due in a whole other week, which is really just generating these outputs for your species, and I'll pepper a few more questions in there for you to answer. And then you'll just enter a Google form that points to the path on Taylor where you've run this. So I'd love to see the generated HTML, make sure that it can fully knit, and then I can just see the products. And then if there's any other issues, I can also run the code, the R Markdown corresponding file. Yeah.
I'm still feeling confused about how to interpret some of the outputs from the various models that we ran in past sections of the lab. And I
Mhm.
don't know if the answer maybe is you don't fully need to interpret them because you're using the curve to decide which one to use, or if there's, like, it seems like we ran a bunch of models and then I don't fully understand like how we're deciding which one to use still.
Yeah, that's totally fair. Yeah, so I'll add more text about that, but essentially it would come down to things like comparing like the area under the curve. If there's some extra stuff, I had mentioned this AIC criteria, and that's if you have the same modeling technique, like a GLM or a GAM, then you can use that criteria within that modeling technique, but it doesn't necessarily apply between modeling techniques. So you could change the input variables or whether you have a smooth parameter, but yeah, the AUC you would compare broadly across any modeling types. Yeah. And then I think it's just that other aspect I mentioned of if maybe a model does a good job predicting based on your test data set, so you get a high AUC value. But if you look at the term plots and there's a lot of like spikes and wiggles and things that you can't ecologically explain in a you know, then maybe you're more interested in ecological kind of interpretability versus predictive power. And that's where you might have some other kind of decision process.
Are we expected to go back and sort of like drop variables that are potentially like autocorrelated?
Yeah, with this lab, you should do that at least with the Maxent model, and that's what this this calibration step 2 of will do for you, which is, you know, here we've got the environmental stack where you're feeding in all of the input predictor layers, and then you're looking at this variance inflation factor, and then you're using this exclude function that basically winnows down the stack based on this variance inflation factor. So this is a new environmental stack that has a reduced set of layers. So I would expect you to run that.
Oh, gotcha. Okay, so what we did before was sort of just to visually just see it, the pairs plot.
Yeah, it was just to see it. And this is a more methodical way to actually go about it. There's a lot of ways of approaching this. So you could just see it from previously running. Like I had you guys do this explore step and just print out the densities. And then you did, let's see, yeah, with the regression, you had this guy. So you might have like seen like, oh, that's high correlation and picked one already and then already removed one. This can get actually pretty involved with a whole bunch of fairly confusing techniques. So I tried to pick the simplest way to kind of winnow this down. But if you really wanted to be more specific, what you might do is run it with altitude. Like, what if I really wanted altitude in there because the literature referenced the altitude? Then maybe I would, rather than just automatically dropping the altitude, what I could do is keep the altitude and drop the bio1 variable and see how is my variance after I drop that. So the functions I shared, you could very easily just drop that from your raster stack, that other layer, and then run that VIF and then see how you're doing. And you could manually also solve that. So that would be another way of approaching it. In a lot of these other modeling techniques, they'll have things like step GAM. So it will actually start with like, there's a whole process of starting with picking the one that has the highest correlation between your predictors in your response. So picking the one predictor, and you could then step forward and then add the next most explanatory variable until you get to something that is a full model, and then compare with that AIC criteria along the way to use the one that has the lowest AIC. Or you could start with the full model with all of them in there and then drop the least explanatory. But it's kind of like that whole stepwise process it can get pretty convoluted, as you can imagine. And so I just suggested this like quite straightforward approach. But that model selection, you can spend your PhD figuring out different ways of doing that, basically. I just want to hint at a larger set of possibilities with that. Yeah.
Gotcha. And then for like the 0.7 thing, does it just drop the one that has like less explanatory power? Or...
Yeah, exactly. And if you look at the VIF, let's see. If you look at the function, there's actually like even this, there's even another way to do it. It doesn't, that one didn't link. I think if I prefix the package, it'll show up. But here's this. So you guys are using VIF and VIF core, but there is this VIF step, and the threshold for the VIF correlation, it corresponds with what we talked about as 0.7, which we see in the literature. This is much less consistent. The actual value for the variance inflation factor, 10 seems to be, but it's kind of a weird number. And this talks about how it kind of steps through. It does a stepwise procedure. VIF first finds a pair of variables which has the maximum correlation, so greater than the threshold, and excludes the one that has the higher VIF. So even though, like if we look at this thing, the highest VIF is altitude. So that's why you see that dropped. So altitude is the most highly correlated to all the variables that are input here. And so that's why it drops that one. And bio one remains so that would be the first one it would drop. And then this was still there. So that's greater than 0.7. So once we dropped this altitude one, then that correlation drops out, and then you're left with this one. And so this is 0.86 between ER tri and then ER topo wet. So because ER tri has a higher overall VIF, then that's probably the one, that gets dropped out. But it would run that VIF score, which the scores would change as soon as you drop out one variable. All of them would change because they're kind of with respect to all other variables that are input.
Gotcha.
So that's why it steps through.
Cool.
Yeah. All right, let me see if I can, I'll just hang out here and fix the schedule. moves.
I have a question when you're done.
Yeah, go for it.
So when that function is deciding which one to drop, which of the which of the 5 variables to drop based on like which has the most correlation with all the other variables, is it considering the variable contribution, which was like a graph that we made in lab 1B? How are those two processes connected?
Oh, good one. Good one. Yep, that's a really good point. So they are not explicitly because the way that we did that model selection was in this case before we do the fitting. So, but that is a really good point because that is another way to do the model selection, meaning, you know, maybe that altitude variable is more important. And so you would hang on to that and see what other variables you could drop out based on that importance value. So that's another way to fully legitimately approach this. So yeah, in this case, we see, okay, so the variable contribution with all the models, all 5 of those variables in, bio2 seems to come out as being contributing the most. But, you know, because of this, you could well argue that bio altitude is more important than dropping bio 1. These two are highly autocorrelated, but maybe I want that one instead of this one. And so that is totally legitimate to select your models based on this variable contribution. And there are modeling approaches that do stepwise do consider that this kind of input in a stepwise fashion. That's a really good point.
But the VIF core function does not consider the variable contribution because it drops it for you based on other criteria.
Exactly. Yep. So it drops it just based on looking at the VIF score and the correlation. So it's going to be less informed about how well that variable. It's not based on how well that variable is contributing to your model explanation, which this would tell you. Yeah. So that's a totally legitimate way, and honestly, kind of preferred way. If you only have a few variables, then that's better. If you've got a lot of variables, then you know, every combination can get a little unwieldy. Yeah.
Okay, thank you.
Let's see. Okay. So I'm just on my machine. And then I'll hop on Taylor.
I have a question when you're done with this, Ben.
Mm-hmm.
I guess I still feel confused about the term plots and exactly like what we are or are not looking for and how we use those.
Mm-hmm. Yeah. Let's see. Let me start this. And then I'll open up a term block. I'll just open a term plot. I'm having trouble there. Okay, so if we look at, we had a bunch of term plots here. So these are really uninteresting. It's a linear model. And usually on this y-axis, it's not ranging from 0 to 1 because it's not yet logit transformed. So remember we have this little connector function. And so this transforms that response to being clamping it from 0 to 1. But if before that, this is like what's called a partial. So the idea is that all other predictors being equal, this is generally how the predictor for altitude here then determines the response. So the signage is correct. It's with this is saying that it's less likely. So it's going down with altitude. So you're less likely to, it's approaching a 0 with increasing altitude. And so that it's more likely to see a presence. So eventually this y-axis converts to a 0 to 1 range. And in this case, just the linear model is just the signage of how that predictor tends to affect your response, the 1 or 0. Now we can see a lot more detail here with the GAM. So GAM allows wiggles, and this is also a rug plot or rugosity. It's like this notion of here's where we actually have data. And you see as where we don't have data, the confidence interval given by the dashed line expands. So we have much less confidence about that negative relationship. And where you have a lot of data, generally the confidence is higher. But that Y you should think of as a response, and your Y, the Y term that we've been talking about of present versus absent. And then the X is the range of values with that predictor.
Hey, Ben.
Mm-hmm.
If the Y is the response term, then why are we getting these large and varied scales numerically on the Y-axis?
Yeah, that's because in these cases here, it's not yet transformed according to this logit function. So this is called a logit link function. And so if you just look at the partial, I guess with the GLM and GAM, I think there are definitely plotting packages that do constrain it and transform that Y, or there might even be arguments for the ones used here. What's interesting is that when you go down to Maxent, because they've made things fairly straightforward, you do see that. I think that it is ranging from 0 to 1. So that's just a transformation issue with the logit.
Thanks.
Mhm.
So are these term plots just kind of like a sneak peek into your data? You can't actually like make any decisions off of them like you can off of like a number output by a function?
So let's see, what would be a decision like, are you wanting to just input any arbitrary value of a single environmental variable and then and get a value back? Or are you thinking that maybe looking at this term plot, like you could actually say, well, this is totally unrealistic. I'm looking for something that adds like ecological interpretability, and this is not this is has a big W and it doesn't make sense. So that could just be an anomaly of the data. Maybe you didn't have too many data points and you discard it because it looks too silly. That's doable, yeah. Or maybe it's an indicator of some outlier data. Maybe there's some bias in where you go and get the data. Like historically one of the biggest bird data sets was the BBC biodiversity bird colony or bird count data set. Anyway, it's a bunch of folks doing a bunch of bird counts on specific days, the specific protocol, but they generally would count close to roads. So is when you'd have a road, like distance to road, with like the closer you are to a road, major road, that the stronger the habitat. And you might just like get that, see that there's bias in the input data and then realize like that's not informative from an ecological perspective. It's just it's a bias. And looking at these term plots can kind of help you tease out some of that stuff.
So what would bias or an outlier point look like on a term plot? Like, could it be like a spike, or like I see in your like topo wet, it seems like it's going between like 1 and 0. So like, are those considered like abnormal shapes that would kind of raise a red flag and instigate you to like look at your data for outliers or bias in collection?
Yeah, it could be. These are not super weird, to be honest. Like this has a little bit of a peak and down, but a lot of times these are just proxies for other things that are more nuanced. And yeah, so yeah, you could try to remove some data and be more specific about where these data points are, but it's telling you how that relationship from that original slide that we were looking at, what that relationship looks like. So it's really getting to this little guy, this cube, what is the statistical relationship? And we can understand what that relationship is by looking at the term plot. So that's peering into the types of values that you get. Yeah.
Okay, thank you.
Mm-hmm. Mm. All right. I'll talk to you guys later. I'll be updating the labs with more explanation.